interested in. And from that, you can figure out what the observed brightness would be given a known background continuum, right? So it doesn't go into the molecular excitation. It just says if we have this excitation, this is what the observations will be. And that's kind of what Trey meant by this like forward process, where we're starting with as far back into the starting point as we can, which is this is what the excitation of the molecule is. This is what the population of those levels are. And then we move forward to predict what the observations would be. And then we compare that to the observations that we have. So I think that's the nuance. That's the difference there. But it's also the limit of it. It's not taking like gas temperatures or anything. So when we're saying things like we assume LTE and all of that, that assumption or lack of that assumption doesn't even come into this kind of code. It's independent of that. But if we assumed that the system was under LTE, then that would allow us to not have to do all of that modeling stuff. Because then the distribution of populations would just be based on a thermal temperature. And then we just use like, Maxwell-Boltzmann stuff that we did in undergrad.
Yeah, but I think that's the problem number one Trey's listed here is assume LTE.
Yeah, it's not an LTE. You
Yeah,
can't.
but it's not. So
It's
as
really
he's
not a
shown.
Paris.
Uh,
It's which brings us so many tears and sadness. Heap, is your hand still up or is it up again?
Is that okay? Sorry,
Oh,
my connection was not stable, so I was kicked out.
oh,
oh, okay. Something
Yeah.
that was.
So I would like to ask again about, of course, these lines, and how about the ratio between the amplitudes of the different lines?
yeah.
If these lines are the same, right? And how about the ratio between the strongest and those lines?
So I'm not sure. Oh yeah, sorry.
If they are in the LTE, or are they would they keep the ratio between the lines the same?
Yes, yes. I mean, without considering there are some like complex, super annoying things about the radiative transfer, which could make that not always true. But in just generally speaking, without getting into more complex effects, yes. In LTE, you would be able to, if you knew the temperature, you'd be able to predict the height of all of those lines, because the height of the lines is a function of the excitation temperature, which is the relative population of the levels, which in LTE that would be equal to the gas temperature. And then also a function of the optical depth, which optical depth itself does have excitation temperature in how it's calculated, but the most important part of optical depth is the column, is how much gas you have. So if really what the height of the lines tells you or could tell you is how many molecules are in each of the levels, or either of the two levels that are involved in the transition. So yeah, if you know what the excitation temperature is by making that assumption that it's in LTE, which means that all the excitation temperatures are the same, then you can work out from what you observe, you can work out what that is. But yeah, they would have to all be their predicted height ratios, which if LTE isn't a valid assumption, then they won't have those predicted, and then everything falls apart.
Yeah, thanks for that. So I'm talking too much, but sorry guys. I just want to ask one more question. Can this be true in the optical wavelengths? I'm thinking about H alpha and H beta. The ratio between the two lines for silicon and N1, for example. The ratio between the two lines should be the same towards the AGN, for example. So if they are not, they do not have the same height, the same amplitude. Do you think that their temperature are not in the same the temperature? And does this apply in the case of the optical wavelength?
I think it's not so much a matter of what wavelength you're looking at, because say if OH had transitions in optical that we could observe, which I don't know, maybe it does, um, it's then a question of is the population of those levels that we're observing transitions between, is there an assumption that those have a similar excitation temperature? That's really what it comes down to. But if something actually is in LTE, if something actually is, if that is true, not just an approximation, but if that is true, that's from my experience. I don't know if this changes if you go to different molecules, but it seems to be more of a function of density and temperature, because in order for the terminology that people use is like, in order for the molecules to thermalize, or the transitions to thermalize, there has to be a certain amount of interaction between the molecules, interaction between all those levels, so that they can come into thermal equilibrium with each other. And there's kind of a threshold density and temperature in general. Although Joe's just turned her video on, I'm sure she's got thoughts.
Well, I've
Used to that.
yeah, I also wanted to throw, I'm not sure whether I can actually raise my hand in this system, but yeah, what I want to say is that in principle, it's we shouldn't talk about LTE, non-LTE. It's like if you consider all these departures, then technically you have to consider all the level diagrams and kinetics and how it actually goes from one level to another and what processes drive it. And in that complex picture, you actually start to see that there are blocks, and you can see like within some blocks of levels, you can consider kind of LTE. It's not just local in terms of the space, it's also which levels you include. And for this analysis, it only matters that you can describe a group of levels with some temperature-like quantity. You can call it temperature. If you have real LTE, then all these things are equivalent to single temperature for the whole system. In practice, of course, like different levels will have different groups of levels will have different temperature, and you can say that there is a gas temperature, there is a radiation temperature, and there will be some balance between them, and you start to get all these weird effects. And when you look at optical lines, they're actually much more probable, the transitions themselves, than most radio lines. And as a result, they actually will have tendency to thermalize much easier. So that's the reason why, like, we have masers, but lasers are kind of harder to create, simply because the energetics is such. So it requires much more energy to maintain that like extreme departure from LTE and too many levels at the higher level of the transition we consider. But in principle, in terms of the math, it's all the same, as long as we take like all effects into account and don't try to oversimplify and ignore certain things.
I suppose that's
Oh,
that's a very good
thanks,
point,
Matt.
of course. But I think when we're in this very real situation of looking at our data and seeing, what can we possibly squeeze out of this data, we then do start to ask questions of like, okay, I know that this is not technically correct, but how wrong will it make me really? And what we do find is that while OH is definitely not an LTE, definitely not. If you assume that the main lines share an excitation temperature, you tend not to be very wrong very often. So that's just a tidbit there. That's why people tend to do that so much. It's not technically correct, but it doesn't have a huge impact on the final answer, which usually they're trying to get at column densities, right? So yeah, it doesn't have it depends on how you feel about making simplifying assumptions.
Just one caveat to that. It does make a big difference to the column densities if you use the assumption of LTE to derive the optical depth, which is a thing that people used to do before everyone realized. Then you get optical depth. Then you get column densities that are out by an order of magnitude. But if you try and solve a degeneracy by assuming that the excitation temperatures can be equated to each other in the two main lines, you do go very wrong. So don't do that. But if you
Thanks, guys. I think I have some I need to have some chats with the Galaxy people optical wavelength with that. Thank you.
Always. I wanted to add too, because I talked a bit about how like the code that I wrote in the code that that I used a lot for my Arecibo data, how it needs like the on-off observations. There actually is a mode of amoeba of my code. I put the paper, it's in the Slack somewhere. I also put it in the chat. There is a mode where it can take just the absorption data and just optical depth spectra, which can be then very useful because it applies some constraints on what it expects the ratio of the optical depths to be. There's a quote rule, like an optical depth sum rule, but I put it in inverted commas because it's not an absolute thing. There's an excitation temperature sum rule with the ground state levels of OH, and that's always true. That's always true because that's because they share the 4 levels, so that there has to be a relationship there. But the optical depth sum rule is more of a applies more often than not kind of thing. So I think from memory, I can't remember because I wrote it a really long time ago. I think it has something like that where it penalizes strong departures from these observationally recognized patterns. But then of course, it's got the satellite line inversion, which is crazy, but it does have that mode, and that was able to recover fairly decent Gaussian decomposition. Of course, you're not able to get the excitation temperatures out of that, so you're not able to constrain the column densities from that, but we were able to identify individual clouds and that sort of thing, so that it has that value.
Great.
Thank you for that.
Oh, sorry, Allison?
No, I was just saying thank you for that and for putting it in there, and we'll definitely check it out. We'll be checking out all of them. Thank you.
No worries. Heap?
And just I mentioned, there's a long conversation with Trey on Slack. You can have a look.
Yeah, I can see it. It's just going ping, ping, ping. Yeah. So yeah, everybody, please jump into that that conversation in Slack, because yeah, he's probably bored on his flight and would love to answer people's questions. But we'll have another session on like the molecular excitation stuff. There's going to be another session on that, and that'll be another forum to talk about these kind of assumptions. So that'll be really good. Something I wanted to ask the people who were here. I have a like it's meant to be like a workshop. It was a 2-hour session that I did at some point on Bayesian, like on Bayes' theorem and that, and it includes an example where it uses MCMC to do like a really, really, really basic Gaussian fit of spectra, but it's meant as a method of learning how Bayesian statistics works. Would anybody find any use in that? I could share that somewhere.
Yeah, I would think so.
Definitely. Thank you.
Okay, cool. Let me dig that up. It's deep within the bowels of my laptop, but I'll find it. I'll find it.
Trey, I think, also has one. I will tag him. Trey.
Oh, he has like a tutorial?
He's like a short presentation on Bayes' theorem. Maybe I'll check with him.
Okay, cool. Yeah, it's one of those things, when you put together a workshop and you only give it once, you're like, I spent so many hours putting together that bloody thing. I get more mileage. Okay, so do we have any, so obviously like if you have any more questions for Trey, Slack is the place to go for that. But if there's not any more questions that anyone wants to ask, are there any more questions or any other discussion points people wanted to talk about here? No, I'll take that as a no. Okay, well, we may as well just end it there then, and everyone can head over to Slack and spam Trey with questions. And yeah, and I'll see you guys in the next session. So thank you very much.
So
Bye.
Thank you all.
Thank you.
There's always a couple of people. There we go.
Oh, we're still recording.
All
Let me
right.
stop that.
Oh.